Today, my presentation is flow through electrochemical separation, purification, the non-uniform polarization, and its environmental implications. First, this is a picture of my unit. It is based in Guangzhou, Hong Kong, uh, Macau, Great Bay. It's on a small island shared by a few universities, and my uni has the largest campus side area in the city town. This is our school, called School of Ecology, Environment, and Resources. When I first introduced my school to Professor David Wade, he commented that it is quite something because our people has very diverse research background. Some people they work on marine science, and the other work on computing. Now we have 47 academic staffs. Now our school is built in the analytic center of the uni. Later this year, we will have a new building. So next time, when you guys with our school, I can treat you in our new building. So today I will discuss about the reuse or the recycling of key resources in especially in Guangzhou. So now our economic capacity is compared to uh, other great places such as Tokyo, New York City, and San Francisco. But the resource utilization efficiency it now is still pretty low uh, in Guangdong. So one example is the water. Now our water reuse rate is far below the national level. Now it is still less than 85%. In 2019, among the over 5K large-scale industry enterprises, no more than 300 have used unconventional water resources. So this would be a problem, especially regarding the uncertainty of from the climate change. So we need to find a new routine to control water pollution while reuse part of water uh, at a minimum energy consumption. So in the past 3 or 4 days, we guys discuss a lot of electrochemical separation especially using the CDI part. But today I will discuss about something different. It's the product side. So similarly, they share the same kind of benefits like chemical free, simple operation, and easy scale up. For the fabric size, so it can generate other merits, such as the generation of high reactive species, such as the oxidative, hydrogen radicals, or the reductive atom hydrogen. But it still has the challenges because the reactive species they only have very short lifetime, so their diffusion path is only like 1 micrometer away from the electrode surface, but the diffusion path for the pollutants it is always more than 100 micrometer. So these problems result in the slow reaction, high energy consumption in traditional flow by system. So likewise, so this is similar to uh, the presentation from Matthew Suss. So in even for the Faraday processes, when we use the flow through electrode, so it can generate some extra benefits, such as it reduces the diffusion layer thickness to the diameter, the pore size of the flow through electrode, and we assume the reaction is not limited by the diffusion process. In Faraday process, we always turn this kind of flow through electrodes, reactive electrochemical membrane. That is the IEM. Over the past 3 years, we have done a few studies on IEM. What's the difference between the fundamental difference between flow-through, that is the IEM electrodes, and the traditional robotic electrodes? For the batch of the flow by mode, we assume it will be severe surface polarization. That is, the reaction only controlled by potential applied onto the surface of the electrode. But for the blue one, because water can pass through, or the reaction occurs inside the electrode, so the potential may decay uh, inside the electrode, thus influencing the redox reactions. So the potential is no more homogeneous in the electrode. So we assume there might be some non-uniform polarization process in the flow-through electrodes. So first, we developed a model to describe the process. It has two assumptions. The first one is the material is uniform. The second one, there will be no concentration polarization inside the electrode because we assume the flow rate is high enough. But for the first assumption, this would be a problem when we prepare some real electrodes, but I will discuss this issue later in this presentation. Now this work has been accepted by EST engineering. So if you like to know more details, you can read through the paper. So the model include 4 parts. Yeah. So we use a model IEM. It is kind of thin oxide. So a few parameters have been included in the model, including the overall potential, that is the potential between the theoretical potential that is required for the Faraday correction and the real minimum potential we need to apply to the electrode to trigger the reactions. So we have prepared a few electrodes for the simulation of the special over potential distribution inside the IEM electrode. So according to the model outputs, we found some key influencing parameters include the pore size. We found the smaller pore size, the faster decay, and the thinner reaction depth. That is the potential rapid decline to a certain value, and below the value, we know the reactions for gluten removal. And the second very significant influencing factor is the solution conductivity. We find one that the lower the solution conductivity, the faster or potential decay was observed, and also resulting in a thinner reaction depth. Interestingly, the initial potential has little effect on the special potential distribution inside the IEM electrode because this term is almost 1 within the overall potential we applied to the system. So the above information is based on the mathematical process. Always we say, okay, we can't directly see whether it is right or wrong. So we use another methods to validate our model and assumptions. Now we use electrochemical imprinting methods. We need to add a probe into the system, and at a certain potential applied onto the surface, there would be either electron deposition or electropolarization process to capture the reaction factors. And we can visualize the results by SEM and the EDX analysis. So we need to find a probe. Yeah, it's core of the process. So we compare a few available probes and lead time we find it is the optimum candidate. It has two reasons. The first one, it has appropriate reaction potential. Uh, at this potential, yeah, so it is the starting uh, potential for oxidation of most micropollutants. And the second benefit is high stability. There will be no further oxidation of lead oxide, and the generated lead oxide has strong binding with the IEM. So according to the visualization results, we find the water flux and the electrode spacing not affect the reaction depths, and the depth is around 300 to 700 to 750 micrometer. And also the visualization results is comparable with the mathematical model output. That is the solution conductivity and the actual pore size significantly affected the reaction depths, while the water flux and the potential applied to control and also the electrode spacing did not. It should be keep in mind. So although when we increased the applied potential onto the IEM, there was no further increase of the reaction depth, but this practice can still increase the reaction because it increased the charge transfer rate and the hydrostatic activity. But essentially, the kinetics uh, and the reaction depths, they are two different kind of things. So we further justify our results from the modeling and the visualization part by oxidizing a few kind of micropollutants in the IEM system. So we found one way scavenging the top layer that can generate hydrogen radicals for the electron-rich micropollutants, for the SMX, BPA, and OR. There would be minimum effects on their oxidation rate. But for the refractory species such as IPP and ATZ, the oxidation rate has been significantly affected. So next, we think how the findings from the non-uniform polarization affect the design of the electrodes. So whether we can reduce the material assumption or optimize the whole design. So we prepared a few steel doped tin oxide IEM electrodes with pore size ranging from several micrometers to tens of micrometers. So we their performance for antibiotics degradation. So and structure function relationship has been observed between the IEM pore size and the purification efficiency. We found the purification efficiency does not constantly increase with a decrease of the pore size, but tends to be stable when the pore size is reduced to a certain value, that is around 27 micrometer in this study. It seems that the findings uh, were not consistent with our knowledge of the enhanced mass transfer and the capacitance of IEM electrodes at a smaller pore size. So we first use a CFD method to simulate the water flow inside the IEMs. And this part of work is collaborated with Dr. Hongjian Zhou. Yes, the IEM we prepared it. Yeah, they present the enhanced mass transfer at a small pore size. So this is correct.
for many years.
But the problem
has a lot
is
of experience.
when we
how numerical modeling
increase the hole size, so the reaction depths decreased, as shown in this slides. The yellow dots are the model results, and the red part represent the reactive zone, catalytic reactive zone, visualized by the lead imprinting methods. So at a smaller hole size, too, we had enhanced mass transfer character of the REM, but the reaction zone only constrained at this very small zone beneath the electrode surface. When we increase the hole size, the mass transfer is a bit slower as compared to small size REM, but they have a larger reaction depth. So we may conclude that the people should think about either the reaction depth, but also the mass transfer inside the REM. So these two parameters are significant factors that have a trade-off effect. Also, our findings can help us to optimize the design of the electrodes. That is to find the most economic thickness of electrodes. We have prepared a few electrodes with thicknesses from 600 micrometer to 3000 micrometer, according to the model and the visualization results. The reaction depth is around 700 to 750 micrometer, and because it has a double side, so the total reaction depth is around 1500 micrometer. So when the electrode thickness below this value, when we increase the electrode thickness, the reaction rate increase. When the electrode thickness larger than this critical value, the threshold, there will be no further increase of oxidation. So we can reduce the electrode the materials by this way. Also, our findings not only limited to the tin oxide we investigated, we also evaluated the performance of other metal oxide electrodes, such as lead oxide and also Ti47, and we find that the reaction depths decrease significantly with the decrease of the bore size below the critical value, resulting in the decrease of the intrinsic oxidation kinetics of the IEM electrode. So these are the take-home messages of this presentation. And so with regard to the electrochemical separation and purification technologies based on periodic reactions, we developed the mathematical model and the visualization methods to review the non-uniform oxidation characteristics of the IEM electrode, and we found the depth of for the formation of hydroxide radical is less than 1% of the total reaction depth, and the indirect electron transfer process is a dominant process, and the most significant influencing factors we found are the pore size and solution conductivity, because certain kind of water solution, the conductivity is determined. Yeah. So you can, okay, yeah, sure, you can add salts and other electrolytes to increase the conductivity, but it's not practical for real application. So on the other side, we can optimize the actual design. These are not very fancy parameters; they are very general parameters. And if you optimize these parameters, it can help us uh, to improve the process performance. So the second message is that we found that the water purification efficiency of the flow-through electrodes does not increase constantly with the decrease of pore size, although the pore size, a smaller pore size significantly increase the transfer, and that is the main benefit of flow-through electrodes as compared to I. So the reason is that the refraction depth of the IEM electrode decreases significantly with the decrease of pore size, resulting in the decrease of the intrinsic oxidation kinetics. And it drive us to focus more on the catalytic activity area of flow-through electrodes instead of the electrochemical active surface area we measured by the CV curves that has been long time discussed in the literature. So this work has been guided by our group leaders, Professor Zhifeng Yang, and also many thanks to my previous postdoctoral supervisor, David Waite, for their support, and also many thanks to our group. They worked really hard to deliver some interesting results, and also many thanks to the National Nature Science Foundation of China, and also the Foundation of Guangdong Province. They provide money. It's also a very important part of research. At the end of the presentation, so I want to add a small a short slide for the new journal. It's called the Journal of Water Technology. Me and also Dr. Matthew Sass, we are on the board. So it's a new journal, and it is very friendly to our people working on CDI and also the chemical processes. We may have a special issue to discuss about the electrochemical process for water purification and the reuse. So any manuscripts will be welcome. So that's it for the presentation, and thanks for listening. All questions will be appreciated.